So we've gone over our sine and our cosine graphs and all of those transformations. And then we looked at some word type applications with our sine regression. And now we're going to continue on because hopefully we recall that sine and cosine are only two of our trig functions. We have other trig functions, which means that we have other graphs. So we're going to look at two of those graphs today. Alright, so we're going to start our tangent just like we did for our sine and our cosine. Let's just make a table of values and kind of see where that gets us. So remember that with our graphs, what are we plugging in for our x values? What type of numbers? Or what do our numbers represent for our trig function? We did them in radians, and radians are what? They're angle, yes? So remember, we're plugging in angle values for any of our trig functions. Agreed? Now, remember that when we're thinking back to our unit circle, right, we don't necessarily have tangent just like on our unit circle. However, hopefully, remember that when we have a triangle, what does tangent equal, or what is the ratio for tangent? So just in general, so like sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. What is tangent?
Opposite over adjacent.
Opposite over adjacent. So then yes, particularly when we're looking at our unit circle, our adjacent is going to be x and our hypotenuse is going to be y. Okay. And then what do we know that our x and our y value are from our unit circle? Yeah, so we know that x is equal to what? Cosine, and y is equal to sine, which tells us that we know that tangent is equal to sine over cosine. So when we're looking for our tangent values, most of us don't just have our tangent values memorized. So what we're going to do is we're going to start with our sine and cosine values and just divide them. Y'all with me? Okay. So normally we start at 0. It's a good spot to start. So if I start at 0, and we think, again, I know that tangent of theta is sine of theta over cosine of theta. Let's think back to our sine graph. When I'm at 0, what y value am I at for sine? Or where does it start? For sine, starts at the origin. So that means that my output is also 0. So sine is going to be 0. And then if I'm thinking about my graph of cosine, well, what does cosine start at? 1. Yeah, so I know that cosine of 0 is 1. Well, what is 0 divided by 1? 0. Easy enough. So our tangent graph will also go through our origin, just like sine did. So far, so good. So what's another angle, so kind of going in order, that would come up next? So again, thinking about radians. Pi over what? 6. We can do that. So this one's going to be not harder, but just a little bit trickier. So remember that we said tangent of whatever our angle is. We can find that by taking sine of that angle divided by cosine of that angle. So what is sine of pi over 6? So it's equivalent to 30 degrees, right? It's my y value. So what is my y value? 1 half, right? Yes? Okay. And then that means that our cosine is the other one. That comes up a lot. What is that? Square root of 3 over 2. Okay with that? Yes? So I'm just taking these values off of my unit circle. Well, notice that we have a complex fraction, so a fraction within a fraction. So in order for us to simplify, we need to multiply by the reciprocal of the denominator. So we end up with this 1 over the square root of 3, which is also the square root of 3 over 3. Now, is that going to be a nice, pretty number to try and graph? You want to try and graph square roots of 3? Probably not. So if we plug it into our calculator, what do we get as the decimal of that? 0.5 something. 578 or 577?
577.
Okay, we'll just do 7. Okay, so we get that. Now remember back to our sine and our cosine. Technically, we can always graph 0.577 if we really wanted to. However, we know that that's not going to be one of our key points, because our key points are going to be the points that are easy to graph. Does that make sense? So we're going to go ahead and kind of like skip over that one. Alright? But next up would be pi over 4. Again, thinking about the same thing, tangent of pi over 4 is going to equal sine of pi over 4 divided by cosine of pi over 4. Well, what is sine of pi over 4? Remember, it's in the middle. Yeah, it's the one that's square root of 2 over 2. Right? And what is cosine of pi over 4? It's the same thing. Well, if I have something divided by itself, what do we get? 1. Well, that's probably going to be one of our key points because 1 is going to be quite easy to graph. Alright, so next up is going to be pi over 2. Okay. So again, remember that basically this time, my sine and my cosine have switched. So sine of pi over 2 is what? So remember that at pi over 2, my sine and my cosine have switched from what they were at 0. At 0. So what is sine of pi over 2 going to be? Any response? Okay. It is. It's 1. So then what does that mean that cosine is? 0. Now what is 1 divided by 0? It's not 0. We can't do it, so how do we say we can't do it without having to like write that out? Not imaginary. Undefined. So I'm going to label this as undefined. Well, that's going to make graphing that a little bit tricky. But it's okay. So then now, remember that we could continue on with any of the angles that we wanted. However, remember we decided that pi over 4 was probably going to be one of our key points because they gave us out 1. So I want to use angles that have reference angles of pi's over 4s. That makes sense? Because those are going to give me the nice pretty numbers that are easy to graph. So what angle in our second quadrant has a reference angle of pi over 4? Not quite. Remember, it's 1 less than our denominator. So it's 3 pi over 4. Alright, so at 3 pi over 4, my values are still going to be square root of 2 over square root of 2. The only difference is in my second quadrant, cosine is negative. So if I have a positive divided by a negative, what am I going to get? A negative. So instead of just 1, I'm going to get negative 1. Okay, so far? Alright. So then after 3 pi over 4, it would be pi. And remember, this is halfway in between. So halfway in between, sine goes back to 0. And cosine, halfway in between, is at its minimum, which is negative 1. But 0 divided by anything still gives us 0. Alright, so then thinking about our third quadrant, what angle in our third quadrant has a reference angle of pi over 4? Mm-hmm. 5 pi over 4. Now in our third quadrant, sine and cosine are both what? Negative. So if I have a negative divided by a negative, what am I going to get? A positive. So I still just get 1. Then we have 3 pi over 2. Yes? Which again is going to be very similar. The only difference this time is that sine will be at its minimum now, so it would be at negative 1. But cosine is still at a 0, which means that at 3 pi over 2 tangent is what? Undefined again. And then in our fourth quadrant, what angle has a reference angle of pi over 4? Remember, it's 2 times the denominator minus 1, so 7 pi over 4. And this time, sine is going to be negative, so I end up with a negative 1. So all I did was make a chart. So let's go ahead and plot some of those points. So I'm going to go ahead and go by pi's over 4s. And then my x-axis, I'm going to go, sorry, my y-axis, I'm going to go by 1/2. Stay with me? So that means that this is pi over 4, 2 pi over 4, which is going to be the same thing as pi over 2, 3 pi over 4, 4 pi over 4, so this is going to be pi. 5 pi over 4, 6 pi over 4, 7 pi over 4, and then 8 pi over 4 would be 2 pi. It's going to be kind of off a little bit. That's okay. Now, remind me, what value did we get at 0? 0. Then we're going to go ahead and skip over our pi over 6 because it was a weird decimal. So what did we get at pi over 4? We got 1. Okay, what did we get at pi over 2? Undefined. We're going to go ahead and skip that for right now. Then what did we get at 3 pi over 4? Negative 1. Then at pi, 0. Then at 5 pi over 4? Then at 3 pi over 2? Undefined. Then we add negative 1, and then at 2 pi, right, we would be back to 0. You know with me? Now let's remind ourselves and think back to some of our other types of graphs that we had. for what that's going to look like on a graph. You can either just like jump over it and it gives us a empty circle, which is also called a non-zero. So if it's like a non-filled in circle, remember we had types of graphs that I would draw a part of my graph, then I had an empty circle, and then I had the rest of my graph. And what do we call that? It's a hole in the graph. So my first option would be to put holes in the graphs. But that's not quite going to work for these graphs because I'm not reducing anything out. What's our other option? Straight lines. Okay.
Oh, wait.
So remember we had those imaginary lines that we put on our graphs that caused us to have breaks in the graph? What were those called? They were the dotted lines that we would draw for our rational functions or for our logarithmic and exponential functions. So this is an A. It's an asymptote. So for our tangent, we're also going to have asymptotes. And we happen to have them anywhere that it's undefined. So we have one at pi over 2 and at 3 pi over 2. And remember that our asymptotes are kind of like black holes. It's going to suck parts of my graph towards those imaginary lines. So our graph looks something like that. Now notice, how often does tangent repeat itself? Every pi, yeah. Notice that at 0 and at pi I'm at a 0. And after that they go up. And then notice that at 2 pi, again I'm at a 0, and it would also continue to go up. Yes? So it's repeating itself every pi. And that's because when we divide that sine by that cosine, it flips it back to a positive. Unlike our sine and our cosine graph, which had to go the complete 2 pi to repeat itself. So what does that tell us about our graph? Or what's it called on the distance of how long it takes to repeat itself? It's the period of our graph. So the period for a tangent is going to be pi instead of 2 pi. So if we were to draw one full cycle, we would start at 0 and we would end at pi. But is that a very pretty graph? Or really even like a whole graph to look at? No, because it cuts it off in weird places, yes? So let's go backwards a little bit and see what we would get there. So notice that if I were to go backwards, I would have negative pi over 4 and negative pi over 2. Well, negative pi over 4, remember we would be going clockwise, so it would be in our fourth quadrant. So we would get the same value that we got for 7 pi over 4. So it would be negative 1. And then negative pi over 2, again, we're going clockwise. So it's going to be our negative y-axis, which would be the same thing as 3 pi over 2. So it's also going to be undefined. So as we start to work our way backwards, I'm still going by pi's over 4. They're just negative now. So we would have negative pi over 4, then negative pi over 2, which we just said is undefined. So it gets an asymptote. And then we said that at negative pi over 4, tangent is negative 1. So is going from negative pi over 2 to pi over 2 a much more complete graph? It's like looking at that section of our graph instead. Yes. So it's a little bit different than our sines and cosines because instead of we're going to start our first cycle at negative pi over 2. And again, the reason for that is because we want that full graph, not like chopping it in half. Okay? But notice that we still have like a pattern, so we can still kind of write out that pattern for us. That way we know what's going to our other graph should look like. So notice that we're going to start at an asymptote. And then our next value is where we're at -1. And normally we would call like that our minimum for our sine and cosine. We can't quite call it a minimum here because my tangent goes on forever. But we can just call it a key point. And we're going to say that that's where y equals -1. And notice after that, halfway in between is our zeros. Then we have another key point. And that's where y equals 1. And then we end with what we started with, which is an asymptote. Yeah, we're all kind of okay with that. So our -1 and our 1 are going to act kind of like our maximums and mins did for our sines and cosines. We just can't call them maxes and mins because they're not. Graphing. No, not quite. Normally we're going to graph some transformations with it as well. So we're going to look at some transformations for our tangent graph. Now, our tangent, the transformations are going to be quite similar to our original sine and cosine function. I still have an a value to the front, a b value on the inside, a c value, and a d value. That a value in the front, we can't technically call it amplitude because amplitude is half the distance from the max to the min. We don't have a maximum and a minimum, but it's still going to stretch it, just like it did for our sine and cosine. The same thing is going to be true for our c and d values. Those are going to give us horizontal and vertical phase shifts. The only thing that's going to be different is our b value still affects the period of our graph, but what did we say the period of our graph is? Pi. So this time, instead of taking 2 pi divided by b, I need to take pi divided by b. Does that kind of make sense? You all with me? Alright, so just like with our sine and cosine graph, I'm going to start by labeling some of our information that we know. So our a value here is 1, which is nice. You don't have to worry about stretching it vertically just yet. And then we don't have any phase shifts. However, we do have a b value. So what is our b value in this case? It's not 2 because remember my b value has to be multiplied. Nope. So if I were to change this to multiplication, what would we get? Dividing by 2 is the same thing as multiplying by 1/2. So our b value is 1/2. So that means that if I wanted to find the period, I would take pi divided by b. So I end up multiplying by the reciprocal, and we get 2 pi. Yeah, with me so far? Now, remember that with our sine and cosine graphs, we also need to figure out where we're going to start and where we're going to stop. And it's a little bit different than our sine and cosine graph because the only thing that affected where we started was if we had a c value. And that was because even if I have 2x equals 0, because 0 is where we normally start, if I divide by 2, I still have 0, yes? But because here we're starting at a negative pi over 2, if we have a b value, it's going to change where we're going to start from. So just like we did with our sine and cosine, we're going to set the inside, so whatever that is, x divided by 2 in this case, equal to where we normally start our first period. And we said that we're going to normally start our first period at negative pi over 2. And then we just solve for x. So in this case, we would multiply both sides by 2. So we get negative pi. So then how would I find my ending value of my first period? So if my starting value is negative pi, and I know the period is how far I go before I repeat itself, how would I figure out where that ending spot is? Yep, I'm going to add my starting spot, which is negative pi, to the period, because that's how far we're going to go before we're done, and that's going to give us our ending value, which is pi in this case. Are we on the page with that? Okay. So notice again, let's go ahead and label. So this is pi over 4. This is negative pi over 4. This can be 1 and negative 1. So notice that I would have to go 1, 2, 3, 4 to be at negative pi. That would be negative 4 pi over 4. Negative pi. So I have an asymptote here, and then we also have an asymptote at pi, because that's where we're going to end. So 1, 2, 3, 4 pi over 4 gives us pi. Okay, so we know we start and we end at an asymptote. And then what's going to be directly in between those two things? The 0. And in this case, I've gone 8 units, so halfway in between is going to be 4 units, which puts us at 0. If we weren't centered, or it wasn't super easy to just kind of look and see, remember that we could always add our starting spot and our ending spot, and then divide by 2. But notice negative pi plus pi is 0. 0 divided by 2 still gives us 0. Then recall that halfway in between our first asymptote and our 0 is going to be when we are at negative 1. And then halfway in between our 0 and our second asymptote is when we're at 1. So notice that we have been stretched horizontally. Questions about that? Yes, no, maybe. Alright, let's look at one more example with tangent. So notice this time we have a b value and we have an a value. So what is our a value this time? Negative 3. And what is our b value? 2. So what is the period of this graph going to be? Pi over 2. Okay. So then our starting spot, again, remind me, what do we set the inside equal to? Negative pi over 2. So we would multiply both sides by a half. So we end up with negative pi over 4. Again, how do we find where our graph is going to end? Plus what? Agreed. So I take my starting spot, I add the period, we have fractions, so I need to find a common denominator. So I would have 2 pi over 4, which is going to give us pi over 4. Agreed? Alright. So I'm going to go ahead and set those up. So we start and end at what type of thing on our graph for tangent? And asymptote. So I'm going to draw my asymptotes at negative pi over 4 and pi over 4. Halfway in between our two asymptotes is what? A 0. But now, be careful, because that 3 is going to stretch us vertically. And it's going to do it kind of the same way we did our maximum. So remember, for our maximum, if I had a 3 up to the front, my point at 1 is now at 3. Now, we don't have a maximum, but we do have a key point at 1. Which means instead of that key point being at 1, it will now be at 3. And instead of our key point being at negative 1, it's now going to be at negative 3. But also, we have a negative out to the front. What does that negative do? It flips it over the x-axis. So instead of being down on the left side and up on the right side, it's going to get reflected. So we're going to be up on the left side and down on the right side. So that is what our graph looks like. And that will be one cycle. Now remember that this goes on forever, so we could always draw more cycles. So it's just going to repeat itself to the left and to the right.